First and foremost, to all of our viewers and listeners, hello, and thank you for tuning in. With us today, we have speaking Rin Irvin, who is a product engineer at AutomationDirect. Rin has written a wonderful article on industrial control system redundancy for Control Engineering magazine, which you can view on our website via the link below. So today, Rin is going to be talking to us about some of the material he covered in that article. And so, hello and welcome, Rin. Thank you for joining us. And to start us out now, if you could just provide our viewers with a brief overview of why redundancy is crucial in industrial automation, and in particular, why it's not merely limited to mission critical applications.
Yeah, thanks, David. So one of the main goals of any automated process is to maintain production, keep your process running, and reduce downtime as much as possible. By implementing some cost-effective redundancy throughout your control system or through your control process, you can better achieve that goal. When some people think of redundancy in control systems, they think of complete redundant control panels that lots of times you'll see in power generation or something like that. And this can be a very expensive and complex system that's not available or necessary for many companies. But there are many different simple solutions that you can do to give yourself a better level of comfort, so that if a piece of equipment does fail or you have a power disruption happens with your system, your processes will continue to run, or you can be alerted through alerted to the problem through your SCADA system or something like that. So.
Very good, yes. And now you also mentioned, of course, in your article that redundancy, it often involves high cost and then increased complexity as well. So it would be great if you could elaborate for the audience on some of the trade-offs designers might face when they're deciding to incorporate redundancy in an industrial automation system.
Yeah, sure. So like you mentioned, there can be many challenges that need to be considered when implementing redundancy into automation. Cost is always first. Does the additional equipment, maintenance, and programming costs justify reducing downtime in the process? Also, more complex systems can cause more difficult troubleshooting, and also more difficult system integration, which then comes back to more cost. The other thing you need to consider is the operators. The operators need to understand the system, how the system works, in addition to, if you're adding in extra failovers, understanding how those work. So there could be an additional learning curve with the training for the system. Another thing that needs to be considered is the physical space. Will adding additional equipment require you to increase the size of your control cabinets? And is the customer dealing with a limited space requirement? So the designers need to achieve a level of system reliability that, while keeping cost acceptable and not introducing too many complexities. So that's kind of those are some of the trade-offs that you need to think about when you're designing these systems.
I see. So it's maintenance. It's the training to be familiar with the new systems that are installed, and then the third one. There was one more point.
Well, cost, of course,
and cost. Yes,
cost
and physical space and physical space.
Physical space.
Yes. Yeah. And now something else that you also discussed that will help set us up for some of the more specific questions to come later in the interview is this concept of single points of failures. So for our audience members who may well be familiar with the concept but could probably use a refresher, tell us a little bit more about why single points of failure are undesirable, and also if you could provide us some examples of how they can actually impact an industrial control system.
Yeah, sure. So, a single point of failure is any element in a system that, if it fails, it can cause the rest of the system or process to stop working. This, of course, should be avoided if possible, or safety should be put in place to reduce the risk of failure. For example, just some of these safeties can be as simple as ensuring that you've got, adequate surge protection and electrical surge, electronic circuit breakers on your control equipment, your field equipment on both the field equipment side and the PLC side, just to ensure that if you do have a overcurrent event or a surge event, that you can protect the PLC inputs or your other control equipment. So the last thing you want is, to blow out a single input and then have to completely stop all production.
Yeah, and that makes perfect sense, of course. You need a bulwark there in case something goes wrong. And so now what I want to do is I want to go into some of the more specific examples you talk about later in your article. So you highlighted various design areas where redundancy can actually be implemented. And I think you touched on power supplies, sensors, PLCs, HMIs, SCADA, and so on. So we're not going to have time to go through all of that today, and I would encourage the viewers who are interested in more of that to read the full article. But do tell us how the benefits of redundancy vary across those different components and what factors influence the decision to implement redundancy in those specific areas.
Okay, so by implementing redundancy, the goal and benefit is to maintain production and keep processes going and reduce downtime as much as possible, like I mentioned before. And also some of the different factors that influence the decision on what to implement consist of cost and complexity. Some of these solutions can be easily implemented, like adding a second sensor to a system into a production system, or also adding on power monitoring. Others can be much more difficult to implement, like adding in redundant I/O, or even going into redundant PLCs.
Very good. So also to get a little bit more into the weeds with one of these specific examples, let's talk in a more narrow way about PLCs now. So PLCs, I think, are typically considered very reliable, but redundancy options do exist, right? So if you could discuss with me and the audience some of the pros and cons of using redundant PLCs versus incorporating just basic hardwired controls, and especially in smaller installations.
Yeah, sure. So PLCs are very reliable and they run for years, if not decades, without any issues. But like you mentioned, there are redundancy options that exist that are commonly used in power generation systems, and also where I used to work, we used redundant PLCs for our sludge incinerators at a wastewater treatment plant. These types of systems are very complex and can be very expensive to implement and maintain. It may not be always a good solution for smaller installations. By implementing power protections and having some of the basic redundancies in place, you can be assured that you have reliable control or have a reliable control system that will continue to run and reduce downtime. By using redundant power supplies and surge protection and all that, you can ensure that your system will run just fine.
I see. And one of the other very salient specific examples you get into are HMI and SCADA systems. So also do the same that you just did for PLCs, and tell the audience a little bit more about some of the complexities of implementing redundancy in networking and visualization interfaces, and how that can enhance overall system reliability.
Yeah, sure. So, as technology evolves and everything becomes more connected, it's more important than ever to ensure safe networking with your industrial network. Being able to connect your remote control processes to the central SCADA system allows for more control and reliability than ever before. If programmed correctly, you can not only have local control at your HMI there locally at the process, but also if you program it, you can also have remote control via your SCADA nodes. In this case, say if a HMI gets damaged out on the floor or out in the field, you can still fully control that system until that a replacement can be installed. Having this type of functionality gives you more flexibility in your systems and improves overall system reliability.
I see. Very good. And so I just have one final question for you before we go. And so, as we've seen and heard throughout our talk and in the article, implementing redundancy, it obviously involves balancing a great deal of factors: price, performance, physical space, as we talked about. So wrap us up by telling us in a nutshell how it is that designers can strike the right balance to ensure improved system uptime without excessive cost and complexity.
Okay. Yeah, there are several factors that the designer should consider when implementing redundancy into their control system. They should identify the critical components and functions that do require a redundancy. They should evaluate the economic impact of downtime versus the cost of implementing any redundancy into their system. Also, consider more emphasis on programming consider more emphasis on performance monitoring and trending to be able to correct any issues before they happen with predictive maintenance. Develop an efficient failover strategy and select critical components where a redundancy plan should be focused. Working with a reliable systems integrator who has experience in providing robust and cost-effective redundancy solutions can be key in any sort of design system.
Okay, and it's a very good summary, and I think here is where we're going to go ahead and draw things down to a close. So, to our audience, if you like this material, I also do encourage you to check out Rin's article on this topic in Control Engineering Magazine, which is linked below, as well as the plethora of other great content Control Engineering Magazine has as well. So thank you, Rin, for taking the time to share your expertise with us. And thank you to the audience for tuning in.
Thank you, David.